A massive NASA satellite is falling back to Earth right now, and its final descent marks the end of a landmark scientific mission. For weeks, its orbit has been decaying, pulling it closer and closer to the dense upper atmosphere, where it will soon meet a spectacular, fiery end. This isn't a sudden emergency, but the long-predicted final chapter for a celebrated explorer of our near-space environment. While most of it will disintegrate into a harmless trail of vapor, scientists say some durable parts might actually survive the crash. NASA has confirmed that the object is a research spacecraft called Van Allen Probe A, and it's making this dramatic, uncontrolled return to Earth after nearly 14 years in space. The satellite, weighing around 1,300 pounds, or nearly 600 kilograms, was one of a pair of identical, heavily shielded spacecraft. Launched together on August 30, 2012, the Van Allen probes, originally known as the Radiation Belt Storm probes, embarked on a mission to study one of the most hazardous and mysterious regions around our planet. The powerful radiation belts, named after their discoverer, American space scientist James Van Allen. These belts are vast zones of energetic charged particles, electrons and protons, captured from the solar wind and held in place by Earth's magnetic field. They act as a sort of planetary defense system, swelling and shrinking in response to solar activity like flares and coronal mass ejections. This dynamic interplay is a key component of what we call space weather. While the belts protect life on Earth from harmful cosmic radiation, they also pose a significant threat to satellites and astronauts, capable of frying sensitive electronics and endangering human health. To survive this punishing environment, the Van Allen probes were specifically designed to be incredibly tough, essentially armored tanks for space science. Flying in a carefully choreographed formation, their mission was to gather unprecedented data from within the belts themselves. Their work led to groundbreaking discoveries, including the astonishing existence of a temporary third radiation belt that appeared and vanished over several weeks. They also revealed the powerful plasma wave processes that accelerate particles within the belts to near light speed, solving a decades-old mystery. After successfully completing its primary and extended missions, Probe A was officially deactivated in October 2019. With its fuel reserves depleted as planned, it was left in a stable but gradually decaying orbit. For years, the gentle but relentless pull of Earth's gravity, combined with the faint drag from the outermost wisps of our atmosphere, has been slowly reeling it in. Now, that long, slow descent is accelerating into its final, fiery re-entry. As the satellite plunges deeper, friction with air molecules will heat its exterior to thousands of degrees Celsius. This intense heating process, known as ablation, will cause most of the spacecraft to burn up and vaporize at an altitude of around 80 kilometers, or 50 miles. The lightweight aluminum structure, delicate solar panels, and sensitive scientific instruments will be the first to go, disintegrating into a trail of incandescent vapor. However, some denser components made of highly resilient materials, like titanium or stainless steel, could survive this inferno. These are often parts like propellant tanks, which are built to withstand high pressures and temperatures, or certain engine components. NASA's analysis suggests that while the vast majority of the satellite's mass will burn up, it's these small, durable fragments that could potentially reach the surface. So, what is the actual risk to people on the ground? Fortunately, it's extremely low. NASA calculates the odds of a piece of falling debris harming any single person on the planet to be about 1 in 4,200. To put that in perspective, you have a far, far greater chance of being struck by lightning in your lifetime. This calculation, known as casualty expectation, considers the amount of surviving debris, its potential impact area, and global population density. The main reason the risk is so low is that the potential debris field is spread over an incredibly vast area. Experts at U.S. Space Command are closely tracking the satellite's descent, but predicting the exact landing spot for an uncontrolled re-entry is nearly impossible until the final hours. This uncertainty comes from slight, unpredictable variations in the upper atmosphere's density, which is constantly affected by solar weather. A burst of solar activity can cause the atmosphere to expand, increasing drag on the satellite and altering its course. Even tiny changes in its orientation or speed can shift the final impact point by hundreds or even thousands of miles. As a result, the predicted impact zone is a long, narrow corridor that wraps around the globe. Scientists say the debris could land almost anywhere along this flight path. However, since over 70% of our planet is covered by water and much of the land is sparsely populated, any surviving pieces will most likely fall harmlessly into the sea, far from any human activity. Uncontrolled re-entries like this are not a new phenomenon. In 1979, the 77-ton Skylab space station fell back to Earth, scattering debris across a remote part of Western Australia with no injuries. More recently, the massive core stages of China's Long March 5B rockets have made similar uncontrolled returns, drawing international scrutiny. While these events capture public attention and raise valid concerns, it's a remarkable fact that in over 60 years of the space age, there has never been a single confirmed case of a person being injured by falling space debris. Still, events like this highlight a growing and urgent challenge: space debris. There are currently thousands of aging, defunct satellites and countless smaller fragments orbiting Earth. This orbital graveyard, a consequence of decades of space exploration, poses a significant collision risk to the active satellites that provide us with everything from GPS navigation and financial transactions to critical weather forecasting. To combat this, international guidelines now recommend that new satellites be designed to deorbit themselves safely at the end of their lives. This is often achieved through a controlled re-entry, where a final engine burn directs the spacecraft to burn up over a designated remote ocean area, like the South Pacific Ocean uninhabited area. Another option is moving the satellite to a stable graveyard orbit, far from operational spacecraft. The Van Allen probe was designed and launched before these guidelines were widely adopted, so it wasn't equipped with a propulsion system for a controlled re-entry. Its return is a natural process, governed by the fundamental laws of physics and orbital mechanics. For now, agencies like the U.S. Space Command's 18th Space Defense Squadron and international partners are using a global network of radars and optical telescopes to track the satellite, refining their predictions as it gets closer. They will provide public updates on the re-entry window, narrowing down the time and location as much as possible in its final hours. Should any debris be found, authorities advise the public not to touch it, as it could be sharp or made of hazardous materials, and to report the finding to local law enforcement. As it makes its final journey home, the satellite's fiery demise will be a spectacular, silent light show for anyone lucky enough to be in the right place at the right time, most likely over an unpopulated stretch of ocean. It's a powerful reminder that even in the vastness of space, what goes up must eventually come down. Nothing stays in orbit forever. The end of this mission closes a brilliant chapter in our understanding of the near-Earth environment. It provided a treasure trove of data that scientists will be studying for years to come. At the same time, its uncontrolled return opens a crucial conversation about our responsibilities in keeping space safe and sustainable for all future generations.